Welcome to OSDU Data Platform Application Developer Training, Wellbore DMS module. The Wellbore DMS is a separate service written in Python that helps managing Wellbore data. It provides type-safe optimized access to your data, and you don't have to parse files after accessing them. It interacts with many OSDU core services. The Wellbore DMS checks access permissions via the entitlement service and can read and write records through the storage service. It uses the search service to find records and fetch them to your application. Finally, it uses blob storage to read and write source file in the Parquet format. It means that no matter what the original file type is, files submitted to the blob storage are going to have a predefined format, Parquet in this case. The Wellbore DMS optimizes the way data is stored and accessed. Before exploring how to work with Wellbore DMS, you need to know that at the moment there are two main versions, version 2 and version 3. Version 2 was developed before R3 release. It works with custom schemas of wells, well bores, well logs, etc. And since R3 release, this is not the preferred way. That's why version 3 is coming. Version 3 works with R3 schemas. Before working with DMS version 2, one should first create schemas for well, well bore, well log, well bore marker set, and well bore trajectory through the schema service. In R3 release, this step can be skipped. Now let's take a look at how to upload a file and create records through the Wellbore DMS. This diagram describes version 2 uploading process, but there is quite the same pipeline for version 3 with a little difference in mapping. We will start with a file in a landing storage that in our case is our local directory. The application starts with reading a file, for instance LAS file, extracting headers and other data pieces from it. The first record to be created is a well record. We run post request to submit all the required information, which may be just the name and the API number. API number is a unique identifier assigned to each well drilled for oil and gas in the United States. Surely, you can provide more detailed information for a well like geolocation. Most of the information comes from LAS file. The well is going to be the parent record for other entities in the storage. To create this parent-child relationship, we are going to use the well record ID that we get back after the well record is successfully created. The next entity we create a record for is Wellbore. You create it in a similar way, but there is an important difference. You should add the relationship field with the well information in it. If we talk about the R3 release, instead of relationship property, you should fill well ID. Next step is creating a log set assigned to the Wellbore. A log set helps to aggregate logs in version 2, but log set is specific for version 2 and not a part of the standard data model, so you can skip this for version 3. Now let's elaborate on how to create relationships between records in this case. So by submitting a log, you provide specific information about this log, for instance, name. And then you add a relationship section that refers to parent entities, where the wellbore will be the parent of the log and the well will be the grandparent. Each entity has the schema, and you will need to specify the relationship according to those schemas. A log set is created in a similar way. In the standard schema, Wellbore ID is used instead of the relationship property. After you create a hierarchy of entities from well to log, you can extract data from the LAS file and submit it to the log. To do this, you make a post request to this endpoint using the ID you got after creating the log. The data is submitted in the request payload as a data frame in JSON format. Under the hood, the DMS gets the record, serializes the data frame into a Parquet file, and then puts the file in the blob storage. As a result, it gets the ID of the file in the blob store and updates the log record with it. So now we have a file in the blob storage and a link to it in the storage record. This step is the same for both version 2 and version 3, because version 3 is still under development. In future, this pipeline may change. That's how we write data via the Wellbore DMS. Note that we use the log as an example, but the similar flow is used for uploading markers and trajectories. Now let's look at how to read data from the storage through Wellbore DMS. Your application will do a request to get the log IDs first. Note that Wellbore DMS provides helper methods for requesting data from the storage. In this example, we can call the query logs endpoint. It will attach the kind as shown here and redirect the query to the search service. So it will filter documents that are going to be returned by a specific kind. There is a similar functionality for other entities such as wells and wellbores. As a result, we get a list of log records. Next, we can extract the IDs to make requests for log data. Note the Wellbore DMS supports the fast query feature, which returns only IDs, not whole objects. To do this request, simply change query for fast query in the URL. Now we have the ID we need, and we can do a GET request to retrieve the log data. The Wellbore DMS fetches the record first to extract the bulk ID that points to an actual file in the blob storage. Then it downloads the file using the cloud-specific library. Next, it reads the file, serializes it to Pandas data frame, and then to a JSON object. This JSON object is passed back to the application. More functionalities can be implemented to the DMS, such as filtering mnemonics from the data. This is useful because typically DMS is going to be deployed in the same cluster as other services, which means it's closer to the storage and faster and more optimized to work with them. There is another service that is a companion service for the Wellbore DMS. It is called Log Recognition Service. It allows to categorize mnemonics into families. For example, you have logs coming from different vendors and they use different nomenclatures. Using the Log Recognition Service, you can categorize mnemonics into specific groups that are called families. You can extend this catalog or create your custom rules to assign families to mnemonics coming to this system. As a result, you can achieve some sort of normalization. For example, you want to get all the gamma ray fields, and instead of fetching every possible name or mnemonic of this column, you can use the family name. Now let's switch to Wellbore DMS demonstration. Here we are going to use Jupyter Notebook. Let me walk through it. This notebook performs as I have just described in the diagrams. So basically, it uses quite a few libraries to access data. And please keep in mind that this is version 2 demonstration. So prerequisites for version 2 are to upload custom schemas. You can find schemas in the Wellbore DMS repository. I have got a sample LAS file from the Kansas Geological Survey. There are plenty of files and metadata is also available for review. And there are several log files attached to it. So here I have a log file downloaded to my workstation. It has some header information as well as parameters and the log data section. In my Jupyter Notebook, I'm using several libraries to manipulate data: JSON, request, to interact with the Wellbore DMS, Pandas, and the last IO library to read this file from the local storage. Here is the Wellbore DMS URL. Next, you can see the parameters I'm using: the data partition ID, ACL groups, and legal tag. They will be put in my records. Provide valid values before proceeding. Also, you need an updated access token to do request. Let's run this section. Now I'm going to read the LAS file. For this purpose, I'm using the last IO library. Here I'm extracting the header information to the well data variable. So here, you can see the same information as the original file, the Wellbore name and the API number. Just to remind you, an API number is a unique identifier assigned to the well drilled in the US, and we can use an API number 10 or 12 for my well and wellbore. Typically, we do not really know the whole information about the specific wellbore, and this file does not really provide information about the wellbore. But I'm skipping these steps to save time, since I know that a well should have an API 10 and a wellbore API 12. But you can also skip the creation step if you know that there are a well and a wellbore related to this LAS file. In this case, you just need to know their IDs. The next code snippet is a helper function. It builds a request payload to be submitted to the Wellbore DMS. So now let's create a well record. Here we populate the well name and API. Then we construct the UWI by removing all dashes and using the first 10 digits. The next step is to specify the location. Well, we cannot use this information in the way it is stored in the LAS file. To make it quicker, I'm skipping the transformation. We have taken the latitude and longitude from the website and hard-coded them in the notebook. But essentially, what you need to do is to convert the location data stored in LAS file to WGS84. Typically, WGS84 is one of the most popular standards for location information. So after the payload is created, you should submit data in the request to the well's endpoint. As a result, we get the record ID. And we're going to use this ID later to fetch this record. And this is how a well record looks like. It has ACLs assigned and the data section. There is also location information that I have submitted and both the name and UWI. So I create a wellbore record in a similar way. And the wellbore record is pretty similar to that of the well. For the UWI, we use API 12. The wellbore has the same location. But what is more important here, you can also see the relationship section that holds the relationship type and the ID. In a similar way, we are creating the log set, which is a collection of logs that I attach to the wellbore. This is pretty much the same, except for that now there are two relationships, well and wellbore. And then I'm going to create a well log record. I am just populating the relationships and set the well name and then getting the record ID back. I'm going to use it to pull the record information or submit the well log data. At the moment, we have all business objects created and we have a list of various records ID that we can use to access this business logic. So in order to submit the log data, I'm extracting the data frame from LAS file and I'm using the orientation. The pandas library does the same. It just tells you which representation is for your dataset that you serialize to JSON. And now I just submit the data to the Wellbore DMS as it is. Similarly, if you run the GET request, I get the pandas data frame and read it from JSON using the same orientation. The last line of the code specifies the range to display as a sample. And now let's try to visualize the data. For this purpose, you can use your favorite library, for example, matplotlib. And we have also included a couple of others for demonstration. This is the Wally library. Here you can get a little better type of charts. And this is the Petropy library that creates little more advanced charts. Here you can see the representation of gamma rays, resistivity, neutron density, and actually you can add more to the template. So, what I have just shown is a relatively easy way to work with the Wellbore DMS. It facilitates data submission, storing, and retrieving. To summarize, unlike the generic API which stores data in the original format, DMS stores it in an optimized way to access your application, and you can easily access data frames, slice, and dice data. It basically helps you to skip transformation and not to think about different variations and different types of data, but you can access data immediately in your application. Besides, you can try the Wellbore DMS version 3. Go to the Labs section and work with Jupyter Notebook. Please note that version 3 is closer to the future state of the Wellbore DMS. Now I'm going over the Wellbore DMS version 3 lab. The first step is pretty much the same. You just need to fill the required parameters. In this lab, we encounter a more realistic example. The difference from version 2 is the record uploading process. Before starting the main part, we upload the well and wellbore via the storage API, because we want to reproduce the situation when the well and wellbore come from another source. Then we also read the LAS file. Next, we find the parent well and wellbore using the search API. Read the descriptions in the lab for more details. Then, to create a well log record, we use the information from both the parent record and the LAS file. Next, we attach data to the well log record and fetch it. We have to use the version 2 endpoint because for now, version 3 does not support these features. And finally, we visualize the data. Thank you.